Hi, I'm Andrew with Nile. Manually tuning Wi-Fi RF often relies on guesswork and repetitive troubleshooting. We change this by using a digital twin to simulate and validate channel plans before they ever impact your production environment. In this demo, the challenge that Nile is solving is RF tuning without the guesswork. A configuration that works well in a quiet office might be terrible on the floor with heavy DFS radar or a dense neighbor network. Traditionally, you deploy the network with best effort configurations, wait for complaints, then iterate in production. With Nile's RF digital twin, we can replay the site's real RF history, try out multiple channel planning variants in a dry run mode, and programmatically compare results before we push changes to APs. This lets us try different algorithm approaches and strategies based on the RF environment. Let's jump into the Nile AIOps Command Center. The RF channel planner is driven by the same platform. This view is driven by an RF digital twin in the cloud. We continuously connect channel load DFS events and AP sensor visibility. What you are seeing is how channels are assigned today under those real RF conditions. In this demo, we will look at a visual version of how A/B testing of channel planner algorithms is performed. Let's start in the channel planner and look at the current RF state for a real floor. This will be our baseline for the A/B trial. This view shows that 5 GHz radios on all the APs across the floor in the 5G channel column is reflecting the existing or current channel plan allocation. In order to test our different algorithm variants, I'm first going to apply the dry run mode to be true. This makes sure that any variant that we are going to try next, the configuration or the settings, are not pushed down to the actual APs, and hence the production network is protected. Now let's look at a few different strategies available to us. There's one simple strategy that basically can go aggressive on non-DFS or weak on non-DFS. Currently, the algorithm parameters seem to be set to weak on non-DFS. What this means is the channel planning algorithm is going to try and allocate as many DFS channels as possible. Let's go ahead and make that aggressive non-DFS. This will make sure that the channel planner algorithm allocates more non-DFS channels. Non-DFS channels in this case would mean channels in the 5 GHz range that fall outside the UNI-2 band. Before we run our new strategy, let's review our existing channels. As you can see, there are a good number of APs that have been allocated DFS channels like the channels 60, 132, 108, 100, 108, and 52. So of the 10 rows that we can see, more than 50% of the rows have been allocated a DFS channel. In order to run the dry run, I'm going to delete the current allocation and trigger a channel planner again. Let's give this some time and come back and check if the new parameters that we just set under the algorithm have taken effect. The dry run mode now has a chance to allocate new channels to all the APs as denoted by the DR allocation. This stands for the setting that has not been pushed down to the production AP. Now let's compare the channels that the APs were on and the new channels that the APs got assigned based on the new strategy. As you can see, some of the APs that are operating on DFS channels, they now have been aggressively moved to non-DFS. The AP that was on channel 132 now says it could be on 153. Similarly, with the APs on 108 and 108 over here have been moved to 165. Although there are a couple APs that are still on DFS channels, as you can see, most of the APs have now been allocated a non-DFS channel based on the strategy selected. So going back to our algorithm parameters to confirm, we had selected a strategy to be aggressive on non-DFS, and that seemed to have worked. Now here's the important part. We are now able to visually compare the proposed plan with the current live channels on a per AP basis. For example, a bunch of these APs that were on DFS channels have now been moved to non-DFS channels in production. Once we see that a particular set of parameters consistently produces a better plan for the site given its radar behavior, for example, neighbor density and client mix, we promote that strategy into a nightly planner profile. The big takeaway is Nile's RF digital twin lets you trial and inspect complex channel planning algorithms against real RF history first, then commit with confidence instead of experimenting directly on users. Nile's digital twin replaces guesswork with automated A B testing and continuous simulation. By validating optimizations against real telemetry before deployment, Nile ensures a reliable network that allows you to autonomously optimize your Wi Fi with absolute confidence.